Hi everyone. Now that we have discussed the step response of integrators and differentiators, and there are so many results and so many circuits that we have analyzed, I thought it's the right point to summarize all these results and then see what we should expect and what they are producing. Okay, so first I'll start off with integrators, and among integrators, we'll first look at inverting integrators. An inverting integrator transfer function can be written as 1 by s tau. For an RC integrator, tau will be RC. For an RL integrator, your tau will be L upon R. Okay. The output voltage can be written as minus 1 over tau minus infinity to t vi of t dt. If I assume that the circuit, usually when we are performing the analysis of circuits, we assume that the circuit is enabled. The inputs are usually applied at t equal to 0. Okay. So if I assume that the circuit inputs are applied only at t equal to 0, then the integral will reduce to something like this. It will be minus 1 upon tau integral 0 to t vi of t dt plus the initial condition, the initial voltage of the initial output voltage. You can express the output voltage in this format. First, we'll analyze what should be the ideal response of an integrator. Right? If I just treat the integrator like a black box, like with a transfer function given by minus 1 by s tau, what should I expect? If I feed a positive step voltage of delta V volts, what should happen to the output? The output should be a ramp, negative ramp. The output should be a ramp but at a negative ramp. It starts at 0, assuming the initial voltage is 0, and then it starts decreasing. And what is the slope with which it will decrease? It will decrease with a slope of delta V by tau with a minus sign. Okay, it will decrease with a slope of delta V by tau. And it will keep on going towards, eventually it will reach minus infinity. Okay, if you wait sufficiently long enough, okay, the more you integrate, the more negative values it will reach, and eventually it will go to minus infinity. So that is if you use an ideal op-amp whose output voltages can go to plus minus infinity. But a practical op-amp, if you use a practical op-amp, at some point you will reach the saturation output voltage and the op-amp's output will saturate at minus Vsat. At this point, once the output saturates, the op-amp will no longer be in the amplification mode, in the negative feedback mode. The circuits, both RL and RC integrators, they reach open loop states. Right? They eventually become, the op-amps will behave like as though they are in open loop. And the outputs will be fixed at minus Vsat. The same thing will happen if I apply a negative step input. What will happen? You should expect for an ideal integrator, if I treat it like a black box with a transfer function of minus 1 by s tau, and I apply a negative step input of value minus delta V, what should happen? I should expect a positive ramp output. And it should keep on increasing with a slope of delta V by tau. Okay, the slope can be found by substituting in this equation. If you substitute your output voltage is simply minus of 1 upon tau delta V, Vi of t times dt, or that for Vi of t will become minus delta of t dt. So that's how you get the slope. Your slope will be plus delta V by t in times multiplied by integral 0 to t dt, which will be t. So you will get a ramp signal which will increase with a slope of delta V by tau seconds. If you assume a saturating nonlinearity, it will just saturate to plus Vsat. Again, no surprises there. Here I have shown the waveform. Starting off at initial condition V0 of 0 minus, output will now start increasing like a ramp signal. So in this region, when the output is increasing as a linear ramp, your op-amp is in negative feedback. Okay? Op-amp operates in the negative feedback region. In this region, once your output saturates, your op-amp will be in open loop. And this is expected for integrators. We said that integrator circuits, especially ideal integrator circuits, will tend to be in open loop in the steady state. So the same thing for non-inverting integrators. I have shown here a non-inverting RC and a non-inverting RL integrator. The general transfer function can be written as 1 plus 1 upon s tau, where tau is the time constant. For an RC integrator, your tau will be RC. For an RL integrator, it will be L upon R. So if you integrate this, if you express this in time domain, you will get an expression that looks like this: Vi of t plus 1 upon tau minus integral to minus infinity to t Vi dt. And if I assume that the input arrives only at t equal to 0, then the integral will run from 0 to t instead of minus infinity to t. And then I should also add the initial condition, V naught of 0 minus here. So this is how the expression will look like. So ideally, if I feed a step input of magnitude delta V volts for these differentiators, assuming the op-amps to be ideal, what should I expect? I should expect a constant term, which means your output should follow the input as it is. Okay, so the output should produce a sudden step of value delta V volts. Then it will also produce an integrated version of the input. It will also produce a ramp signal when you add the ramp to this. So you should ideally add the two signals. This part, so the output signal will have two components, the proportional part and the integral part. Integral part will rise linearly like this with a slope of delta V upon tau. So if you add the two terms, the overall voltage will look like this. It will jump to delta V and then remain constant. For an ideal integrator, this should have blown up to infinity. For a practical integrator with a saturation limit, this will saturate to plus Vsat, which is what I've shown here. The op-amp circuit, the integrator circuit that we are seeing here. So if you observe this expression, I've drawn this non-inverting integrator in a nice way so that you can see the output voltage of this op-amp is equal to the capacitor's voltage plus the resistor's voltage. The resistor's voltage denotes the proportional part. The capacitor's voltage denotes the integral part. Okay, the resistor's voltage will suddenly jump by delta V volts. That's what we already analyzed this circuit before itself, and we showed that the output in one of the previous lectures, the capacitor will suddenly act like a short circuit. There will be negative feedback and output will suddenly jump to delta V volts. After that, a current will be set in the resistor and that current will start flowing through the capacitor, and so the capacitor voltage will linearly ramp up. So that's what we are showing here. So the circuit enters negative feedback at t equal to 0 plus. At t equal to 0 itself, it enters negative feedback and stays in negative feedback till the output saturates. After this, once the output saturates, your op-amp will be in open loop. So there is no negative feedback anymore. And the output will be saturated at plus Vsat. And we showed what will happen to the voltage across the resistor and all that. We showed that eventually the voltage across the resistor will eventually come to 0 and all that. Okay, so the output of the capacitor will be saturated to plus Vsat and the cap will be charged to plus Vsat volts. Okay, so that's the behavior of a non-ideal non-inverting integrator. Okay, so it will have a sudden jump. This is mainly due to the proportional path. That's why the sudden jump is present. If you recall from an inverting integrator, there was no proportional term. So there was no sudden jump. It was always ramping up. Here you see a jump and then a ramp. The jump is due to the proportional path and the ramp is because of the capacitor's integrating action or the integrator action of the circuit. So the next part of in the next half of the lectures, we spoke in great detail about differentiator circuits. We spoke about negative differentiators, inverting differentiators, both RL and RC inverting differentiators. We said that the transfer functions for both these circuits can be expressed in this format. V0 by Vs, V0 by Vi in Laplacian domain can be written as minus of S tau, where tau will be RC or L by R, okay, depending on your circuit. So ideally, if I feed a step input to a differentiator, to a inverting differentiator, I should expect an impulse. And what will be the magnitude of that impulse? See, usually when I write the magnitude of the impulse, or the magnitude denotes the area, if you integrate this impulse, this is the area you should get. So the magnitude, when you are applying a step input, if you apply a step input of magnitude delta V volts, the area of the weight of this impulse will simply be equal to minus delta V times tau. And that follows from this expression. When your transfer function multiplies your output by tau minus tau, and for an impulse, the weight of an impulse is proportional to the step input as well. If you differentiate this waveform, you should get an impulse ideally. But what did we observe in the last two lectures? That if you apply a step input, because of the saturating nonlinearity of the op-amp, so here you will get an impulse if your op-amp was an ideal op-amp, where the output voltage can go to infinite voltages. You will end up getting an impulse. But because your op-amp's output is saturated, so what we in fact see in practice in the actual RC differentiator circuits is a negative pulse of duration t on seconds, and we derived a mathematical expression for t on for inverting differentiators as well. Okay, we did a detailed analysis and we showed this is what you should expect. So an inverting differentiator with a transfer function of minus s tau will respond only when there is a sudden change in the input. In the steady state, there is no change in the input, so therefore output goes to 0. It's just a derivative of this. If you differentiate this, you should get 0 here. Instead of producing an impulse, we ended up getting a pulse, and this is because your output is saturated. Okay, saturated to a fixed value of minus Vsat. And finally, we spoke about non-inverting differentiators whose transfer function can be expressed in this form 1 plus s tau for RL or RC integrators, RL or RC differentiators. And in time domain, it can be written as V0 is Vi plus tau times dVi by dt. Okay, so ideally, if you apply this step input to a non-inverting differentiator, you should get a waveform that looks like this. You should get a constant waveform, a constant step input, okay, the same, which is same as the input signal, plus an impulse signal riding on top of it at t equal to 0. So this is the impulse at t equal to 0, and the magnitude of the impulse should be delta V times tau times delta t. Okay, the magnitude of the weight of the impulse will be delta V times tau. This is what we should expect, but what we see instead, we see the waveform appearing like a pulse. It initially jumps to V plus Vsat instead of delta V, and I can split it up as two components as I've discussed before. So the output jumps to delta V. This is due to the proportional part, the V0 equal to Vi part, and this part is the response due to the differentiation operation. Instead of producing an impulse, the output produces a pulse of width Vsat minus delta V. You can see here itself, and the value of the on time is given by tau ln of Vsat by Vsat minus delta V. Okay, you can see from this expression one very interesting thing. What happens when Vsat tends to infinity? If Vsat tends to infinity, the amplitude of the pulse will go to infinity, and the width of this pulse, the width of the pulse will shrink to 0. You can apply Vsat tending to infinity in this result. You will get ln of Vsat upon Vsat. Vsat is so large compared to delta V that I can ignore it. You will end up getting ln of 1, which is 0. So it will actually approach an impulse. That's what this equation is telling us. Okay, so the waveforms make perfect sense. Ideally, you should have gotten an impulse, but because of the output saturating to a finite value Vsat, we ended up getting a positive pulse with a finite on time. Okay, the higher the saturation voltage, the smaller will be the width of this pulse. So that's how you interpret all these results. So now that we have performed a very detailed analysis of detailed step response analysis of integrators and differentiators, we will now follow it up with the pulse response of integrators and differentiators. Thank you.